In this video, we are going to be discussing the topics in Chapter 7, which talks about chemical quantities and reactions. When it comes to chemical quantities, we need to discuss the concept of the mole and understand that the concept of the mole refers to a measurement for chemical items. For example, particles, molecules, atoms, etc. So, how can we relate the concept of the mole to something that we utilize in every day? Because when you go to the store, you never go and buy a mole of milk. You don't buy a mole of bananas. Now, could you do it? Yes, but that's going to be a very large amount, as you're going to see in a few minutes. Understand that the concept of the mole, because we're counting things in the chemical world, is going to have a specific value. But conceptually, is going to be very similar to maybe things that you encounter in everyday life. So, for example, if you're talking about a case of soda, that refers typically to 24 cans. If you have a gross of pencils, that's going to be 144 pencils. If you buy a ream of paper, that refers to 500 sheets. And as we know, if you have a dozen of anything, including eggs, that's going to be 12 objects. Now, moles are similar conceptually because now we are going to have a specific number of items when we're talking about the chemical world. So, when it comes to the mole, understand that that specific number that I just discussed previously that we know for things that we use in everyday life, in terms of a mole is going to equal 6.022 times 10 to the 23rd items. As I explained in the previous slide, those items in chemistry is going to be particles, atoms, molecules, or even ions, okay? Because when we are in chemistry, remember that we are visualizing those elements in the periodic table or those compounds that we're working with differently, okay? So understand that that number 6.022 times 10 to the 23rd is known as Avogadro's number. In one day, when I was shopping, specifically at Trader Joe's, is one of my favorite stores, one of the things that I observed was in their guacamole, they actually have an image of a person. And this is not the person that invented guacamole or anything. It's actually kind of like a silly chemistry joke that refers to the guacamole or the guacamole. So you can actually look it up online. But understand that the image of that person right there is actually Avogadro, the person that made the discovery of this chemical quantity. Now, when it comes to a mole in terms of elements, as you can see, if we have 1 mole of element, it's going to equal that value, 6.022 times 10 to the 23rd atoms of that particular element. Now, you can have 1 mole of any element. As you can see, 1 mole of carbon is going to equal 6.022 times 10 to the 23rd atoms of that carbon. We can have 1 mole of sodium, and it's also going to equal Avogadro's number, which is 6.022 times 10 to the 23rd atoms. So at times, students are like, but how is it going to equal the same element? Because understand that the difference between the elements is going to rely at the level of the grams. So one of the things that I want you to observe is that this image in the bottom also represents 1 mole of an element. But if we look at the values that are in the bottom, okay, here we have represented a mole of zinc, a mole of carbon, a mole of magnesium, and even a mole of copper. Now, if we have the gram relationship for 1 mole and our elements, As you can see, that number that is in the bottom in grams refers to the atomic mass for that element. So what does that mean? I'm going to introduce this concept early. 1 mole of an element equals Avogadro's numbers, 6.022 times 10 to the 23rd atoms of that particular element. But understand that 1 mole of an element is also related to the grams of an element by understanding that 1 mole of an element is going to equal to the atomic mass of that element. So that's why when we're talking about molar mass, as we're going to see later in this chapter, we refer to it as grams per mole because we're talking about the grams of an element, okay, in terms of moles, okay? So this is just an introduction of how we have that concept of the mole, okay? So the first thing that we're going to learn in this chapter is how to convert from moles to molecules of a particular compound or element, and vice versa, going from molecules to moles, okay? Maybe some of you may be wondering, why do I need to know how to do this conversion? In the laboratory, at times it is important that we know at the atomic level how many molecules are actually going to be interacting of a particular element or even a particular compound with, for example, things in the body. So at times we're going to have interactions between biomolecules and compounds or even elements, and we need to count them. But because we're talking about chemical concepts, we need to count them as molecules or ions or particles, and we need to relate it in terms of moles. So that's why it's very important. So in this problem, as you can see, we are doing the conversion from moles to molecules. The problem reads, how many carbon dioxide molecules are in 0.50 moles of carbon dioxide? So as you can see, what is given is the moles of CO2. What you need to find are the molecules of CO2. So understand that when it comes to the concepts in this chapter, it is very important that you know how to use the following flowchart, because this flowchart is going to guide you to know what are going to be the conversion factors utilized and what type of mathematical operation you need to do. So for example, if I label the information given in this flowchart, again, I have moles of compound given, and I need to find molecules of that compound. So that means that the conversion that I have to do is down here, okay? Over the double-headed arrow, as you can see, I'm going to highlight it in green. That's going to be my conversion factor. In addition, as you can see, we have the steps of how to solve this problem on the left side of the slide. I already stated what is given and what is needed. I already did the plan of how to convert it. I understand that Avogadro's number, which I highlighted in green, is going to be my conversion factor. So I'm going to proceed to set up the problem. So I'm going to read the amount that was given to me. 0.50 moles of CO2. And because I only have one conversion factor, then I'm only going to write one line. And remember, whenever we have conversions, we can set it up as an equality in the form of a fraction. So my conversion here, because I'm utilizing Avogadro's number, understand that I'm going to say 1 mole of CO2 equals 6.022 times 10 to the 23rd molecules of CO2. Okay, so this conversion I'm going to place as a fraction right there. And whenever we're going from moles of a compound to molecules of a compound, understand that we're going to multiply by Avogadro's number. So every time we're doing a conversion in the forward direction, we're going to multiply by Avogadro's number. And understand that if you're given molecules and you need to find moles, if you're going in this direction, then division is what is required. So to set up the problem, I'm going to say 1 mole of carbon dioxide, and over the line, I'm going to put 6.022 times 10 to the 23rd molecules. I'm just going to put MOLEC for molecules of CO2. That's just because of space. And understand that I need to report the correct number of sig figs here, because this value has 2 sig figs. My final answer needs to have 2 sig figs. So when I multiply 6.022 times 10 to the 23rd times 0.50, and I round it to 2 significant figures, I have 3.0 times 10 to the 23rd molecules of CO2 present in 0.50 moles of CO2. In the in-class worksheet, we actually have more practice problems, but in order to at least practice a little bit more of this conversion, as you can see, I decided to solve in this video problem 1 and problem 4. You can go ahead and do 2 and 3 on your own. So as you can see, the first problem, it says how many molecules are in 2.00 moles of water. Okay, so what is given is moles of a compound. What I need to find is going to be molecules of that compound. Again, similar to what we did here in the example, because I was given moles and I need to find molecules. So I'm going in this direction. I'm going to multiply by Avogadro's number. So when I set out the problem, I put in 2.00 moles of H2O. I know that I'm going to multiply by Avogadro, so on top I say, or I write down 6.022 times 10 to the 23rd molecules of water. And in the bottom, that's going to equal 1 mole of water. So when I do this operation, 6.022 times 10 to the 23rd times 2, and I round it to 3 sig figs, then I'm going to have as a final result 1.20 times 10 to the 24 molecules of H2O. Now, the conversion between moles and molecules can also happen for elements. And as you can see in problem 4, we're trying to find, given the number of atoms for an element, in this case 7.46 times 10 to the 23rd atoms of carbon, we're trying to find moles of carbon. So for this problem, we're going to be using this part of my flowchart. What I'm given is the atoms, okay, of an element. What I need to find is the moles of an element. So here, again, I'm going to utilize my Avogadro's number as my conversion factor. And if we are given atoms and we're trying to find moles, remember that we're going to divide by Avogadro's number. Okay? So when I set up this problem, I write down 7.46 times 10 to the 23rd atoms of carbon. I'm going to divide by Avogadro's number, 6.022 times 10 to the 23rd atoms of carbon. On top, I'm going to write 1 mole of carbon, because remember, that is the equality between moles and the number of atoms, Avogadro's number. So when this happens, and we can cancel units in the top one. Here, we just have to do this. Atoms of carbon, cancel with atoms of carbon. So the final answer is going to be in moles of carbon. So when I take 7.46 times 10 to the 23rd and divide it by 6.022 times 10 to the 23rd, then I see that rounding my answer to 3 sig figs is going to be 1.24 moles of carbon are present in 7.46 times 10 to the 23rd atoms of carbon. The next concept that we need to study is understanding how a chemical formula for a compound can be related to the number of atoms and even the number of moles that we have for each of the elements that you may have in that chemical compound. So as you can see here, the subscripts of that chemical formula are going to be indicating, if I'm talking about one molecule of a compound, how many atoms of that compound I'm going to have based on the subscripts. But what we're going to focus now is going to be in the molar amount, because that's what we're talking about in this chapter. So understand that if you have 1 mole of your compound, and understand that in here we're talking about, as an example, aspirin, which has a chemical formula of C9H8O4. What we're doing at the end of the day is that, remember, those values that we have for the subscript is going to refer to the number of moles that we have for that element in this chemical formula. So for aspirin, if we are talking about 1 mole of compound, that corresponds to 9 moles of carbon because it's C9, 8 moles of hydrogens because we have an H8, and lastly 4 moles of oxygen because we have O4. So why is this important? Because at times we have to calculate specifically the atoms that we have of an element given the moles of a compound. Okay, so if we look at the following problem, it asks how many atoms of oxygen specifically are in 0.150 moles of aspirin. Okay, so utilizing again my flow chart, I'm going to state what is given and what is needed. As you can see in the blue boxes, it's just illustrating what is given and what is needed, but I'm going to also write it in the flow chart. So when it comes to the flow chart, as you can see, moles of compound is what is given. What you need to find is going to be atoms of an element, which is here. Okay, so what that means is that in order to accomplish this problem, I'm just going to circle this area. I'm going to highlight it. We are going to do, in this case, 2 conversion factors. My first conversion factor will be utilizing the formula subscripts. The second conversion factor would be the use of Avogadro's number. And I'm going to highlight that in green. Okay? So now that I know that I need those two conversion factors, then I'm going to set up the problem. I'm going to write first the number that is given, which is 0.150 moles of aspirin and remember aspirin is C9H8O4. And since I know that I need two conversion factors, I'm going to set up these two lines. And remember that those lines are just going to represent in a fraction form those conversion factors that I have. So the first conversion factor is going to be utilizing the formula subscripts, which establishes that in 1 mole of compound, that is going to equal specifically the subscript value for the element that I'm interested in, that in this case is 4. So I know that 1 mole of compound, because I'm interested in the oxygen, is going to equal 4 moles of oxygen. Now, in my second conversion factor, I'm going to be utilizing Avogadro's number, but as you can see, I'm talking about the element that I'm interested in, so oxygen. So in 1 mole of oxygen, that is going to equal 6.022 times 10 to the 23rd atoms of oxygen. So now that I have my two conversion factors, I can set up the problem. So here, as I'm moving up from moles of compound, okay, to moles of element, understand that I'm going to multiply by the formula subscript. So I know that in the bottom, I need to match the unit given because I'm going to cancel them diagonally. So down here, I'm going to write 1 mole of C9H8O4. And on top, I'm going to write what is equal to 4 moles of oxygen. Then in the next box, I'm going to write the second conversion factor. Remember that I'm trying to cancel moles of oxygen. So in the bottom, I'm going to write 1 mole of oxygen. And on top, Avogadro's number, 6.022 times 10 to the 23rd atoms of oxygen. Okay? So when I do this problem, moles of compound and moles of compound cancel, moles of oxygen and moles of oxygen cancel. Because this has 3 sig figs, my final answer needs to have 3 significant figures. And in order to do this, I'm going to multiply everything in the top, dividing by the result of multiplying everything by the bottom. But in this problem, I'm multiplying in the denominator 1 by 1. So all I have to do is say 0.150 times 4 times 6.022 times 10 to the 23rd. And that gives me a result, when I round it to 3 sig figs, of 3.61 times 10 to the 23rd, and in this case, atoms of oxygen. Now, one of the things that we also need to understand when it comes to molar quantities is that in molar quantities, as we increase the number of atoms in a particular compound, when we look at what does that refer to in terms of 1 mole, we see that the amount in grams appears to be larger. And we can see that in this picture. In this image, we have 1 mole of either elements or compounds. So my elements, as you can see, I have sulfur and iron. My compounds, I have sodium chloride, I got potassium dichromate, and this is table sugar. So because, as you can see, moving left to right, we are increasing the number of atoms, it appears that all of a sudden we are increasing the amount of matter that we have there. And the reason is because there is a correlation, as I introduced a few moments ago, between moles and grams. So understand, if we focus on this portion of the relationship, that if we have 1 mole of element, the relationship between moles and grams for a particular element comes from the atomic mass that is in the periodic table. So as you can see here, as we focus in the following elements, silver, carbon, and sulfur, understand that, as you can see in the bottom, I'm just going to zoom in. 1 mole of silver atoms is going to have a mass of 1.07, or sorry, 107.9 grams, which it is the atomic mass for the element. And that is true for any element in the periodic table. The relationship between 1 mole and grams is going to be the atomic mass for the element. You may ask yourself, why do we need that? Well, that specifically has to do with the calculation of molar mass. So, when it comes to the calculation of molar mass, understand that all we have to do in order to accomplish this is going to be specifically looking at the chemical formula that we have. And as you can see here, we have to calculate the molar mass for lithium carbonate. So lithium carbonate is going to be Li2CO3. So first we establish the elements that are there. Li, lithium, and then C for carbon, and O for oxygen. Then utilizing the subscripts, we're going to determine how many of each of these elements we have. So as you can see, we have 2 lithiums, we have 1 carbon, because there is a 1, it's just that it is omitted, and we have 3 oxygens. Now, when we do this, understand that one of the things that we are going to be illustrating is specifically that now we go to our periodic table, and utilizing our periodic table, we can actually find the mass for each of those elements, okay? And then we are going to multiply it by that amount that it is present of them based on the subscript. So for lithium, the mass of it is going to be 6.941 AMU for atomic mass unit. For carbon, we have 12.0107 AMU. And lastly, for oxygen, we have 15.9994 AMU. Let's do the multiplications. 1 times 12.0107 is the same value. Then we have 6.941 times 2. That is 13.882 AMU. 15.9994 times 3. That's going to equal 47.9982 AMU. And then to finally calculate that molar mass for a particular compound, all we're going to do is to add these 3 values. So when we add these 3 values, we find 73.8909 But if we report the correct number of sig figs, remember that in addition, we need to report as the final value the number of least decimal places. So if we round it to 3 decimal places, our final value is going to be 73.891 AMU as the mass for lithium carbonate. The previous problem in which we were doing moles of compound to atoms of an element, understand that we have examples. So that's part B in the worksheet. I'm just going to work out one problem so at least you see it. So again, this is where we go from specifically what I explained a few moments ago on how to do specifically given the moles of a compound going to atoms of an element. So let me just do one problem so at least you see that practice. So as you can see, part B, it says how many molecules of oxygen are in 3.45 moles of water. So remember that here we're given moles of compound. We need to find atoms of an element. We have a formula subscript as the first conversion. The second conversion is going to be Avogadro's number. We're going to be writing the number that is given to us. 3.45 moles of H2O. We have two conversions. As you can see, the first conversion is going to be the formula subscript, which establishes that in 1 mole of H2O, we have, based on the subscript, 1 mole of oxygen. And then in 1 mole of oxygen, we have Avogadro's number, 6.022 times 10 to the 23rd. And this is going to be molecules of oxygen. And when we multiply 3.45 times Avogadro's number and then we divide it by 1, we find that there's 2.08 times 10 to the 24 molecules of oxygen in 3.45 moles of water.